ladies and gentlemen, we're going to do 9.5a today. We're going to be doing the alternating series test. So our objectives are that we're going to use the alternating series test to determine whether or not an infinite series converges, and then we're going to use the alternating series remainder to approximate the sum of an alternating series. Alrighty, so let's just start by, it's very echoey in here. So we're going to start by talking about what does an alternating series look like. And an alternating series means that it's going to have alternating signs. So it might look something like the sum from n equals 0 to infinity of a negative 1/2 raised to the n. Well, then I could break this one up as the sum from n equals 0 to infinity of a negative 1 to the n of 1 over 2 to the n, or I could have written it as 1 times 1/2 raised to the n. Either would have been okay. And then if I did that, I would have 1 minus 1/2 plus 1/4 minus 1/8 plus 1 over 16, etc., etc. All right? This particular one is an alternating geometric series. And in this case, r is going to equal a negative 1/2. And then we can talk about whether it converged or diverged based on what r is. And remember, then we would want to talk about the absolute value of r. So now let's talk about the alternating series test. So for our alternating series test, alrighty, so a sub n has to be positive. And then the alternating series, we're going to have the sum from n equals 1 to infinity of a negative 1 raised to the n times a sub n. And it could also look like n equals 1 to infinity of a negative 1 raised to the n plus 1 times a sub n. These are going to converge if, number one, the limit of a sub n as n approaches infinity is equal to 0. And then the second one would be a sub n plus 1 is the next term is smaller than the current term for all n. Okay, so that would be the criteria for our alternating series test. So now let's start by doing some examples. So all of our examples say determine whether the series converges or diverges. So in the interest of time, I'm not going to write that down, but those are our directions. And so our particular series is going to be n is equal to 1 to infinity of a negative 1 to the n plus 1 times 1 over n. Alrighty, so when I take the limit, I kind of ignore the alternating part. So I ignore the alternating sign part, and I just want to consider a sub n. So if I think about the limit as n approaches infinity of 1 over n, well, this goes to 0. So then I have met the first condition. So the first condition said that the limit had to be equal to 0. So then I want to show that the next term is smaller than the previous term. So I'm going to say a sub n is equal to 1 over n, and a sub n plus 1 is going to equal 1 over n plus 1. Well, then I just want to show that a to the n plus 1 is going to be less than a sub n. And if you think about that, as the denominator gets larger, even if it's just larger by 1, this is going to be a smaller number than this one, and then we would say, therefore, the series is going to converge. All right, so one down, a couple to go. All right, let me turn the page so I don't screw something up. For our next example, and that piece of paper just slid out into the hall, I want to, again, determine whether the series converges or diverges. I'm not going to write that down, but I want to go from n is equal to 1 to infinity of n over a negative 2 raised to the n minus 1. So I'm going to say that a sub n is equal to n over 2 to the n minus 1, and then my a sub n plus 1 is going to equal n plus 1 over 2 to the n plus 1 minus 1. So I'm substituting in my n plus 1 up here. Okay, I forgot the dividing line. So this is equal to n plus 1 over 2 to the n. Okay, so in this particular case, when we want to look at comparing our a sub n plus 1 and our a sub n, this is an exponential function, and this is a linear function. The exponential function is going to grow significantly faster. Therefore, the next term is smaller than the previous term, and so this meets the second condition. So this meets the second condition. And I don't know that if you were doing this on an FRQ that you would actually have to write this statement, but you could show this. And if you have this, then everybody understands what you're trying to prove. And then if I took the limit of, as n approaches infinity, of my x over 2 to the x minus 1, well, this is going to approach 0 because the denominator is growing faster than the numerator. And so then I can say the limit as, oops, that's supposed to be an x, my bad, as n approaches infinity of n over n plus 1 over 2 to the n is equal to 0. And then this meets our first condition, and I'm just writing it down just so you can see it. Therefore, the series converges. And I think if I were doing an FRQ, I would probably take the time to write out, therefore. These are from my old geometry days of doing proofs, which my basis students have never done. Sad day. But that's what this statement says. But maybe not all people have taught geometry, so then maybe we should write the words therefore instead of our three little dots. So we have a couple of unique situations that we want to look at. And the first of these situations would be the sum from n equals 1, let me scoot it up so I don't run out of room, to infinity of a negative 1 to the n plus 1 over n plus 1 over n. Alrighty, and remember when we're looking at these, we don't want to consider the sign change as we manage our function, but for right now, let's go ahead and generate those terms. Minus 3 over 2 plus 4 over 3 minus 5 over 4. So this is actually kind of cool because you can see what's going on here. So that's kind of cool. So we know that the next term is less than or equal to a sub n, but, so I've satisfied my condition of the second being less than the first. But if I take the limit as n approaches infinity of n plus 1 over n, this is going to be 1 plus 0, so this is 1. And so this doesn't pass the first test because the limit had to be what? So it doesn't satisfy that first condition. Therefore, since this doesn't work, since this is the first condition, and I'm just going to write first condition not met, and just so you can talk back to me, the first condition was that the limit had to be 0, but in this one our limit is not 0, therefore the first condition was not met, therefore, and remember again, we should probably take the time to write out the words, therefore the series diverges. Alright, the second unique situation, see if I can get this to scoot up just a little bit, would be what if I have 2 over 1 minus 1 over 1 plus 2 over 2 minus 1 half plus 2 over 3 minus a third plus 2 over 4 minus a fourth. So that's kind of a crazy looking sequence. So it passes the first condition. So if we were to manage this one, it would pass the first test or the first condition. And that would be that the limit of a sub n as n approached infinity would equal 0, but it doesn't pass, so doesn't pass the second condition, and the second condition was the fact that the next term is less than or equal to the previous term. Well, it passes the first, but it doesn't pass the second. Therefore, love those three little dots, the series diverges. All right, so that was kind of a unique and special situation. All righty, just a little bit more, and then we will be done for today, you lucky dogs. So the next thing that we're going to talk about is an alternating series remainder. And it is a lovely rainy afternoon. We don't get that very often in Flagstaff. So for this particular situation, it says for a convergent alternating series, S sub n, and remember this is our partial sum. I got to go riding in the rain yesterday. It was lovely, a little muddy, but lovely. Can approximate the sums of the series. And then we're going to have the error involved because, again, I'm approximating and using S is approximately equal to S sub n is the remainder. R of n is equal to S minus S sub n. Okay? Alrighty, so this is a way, sorry, brain and mouth, to approximate the sum of a series by using the difference or the error between the actual sum and the partial sum. Okay? So we have a theorem, and it's called the alternating series remainder. And it is going to be used for a convergent alternating series. So if it's divergent, then this wouldn't work. And if it was divergent, it wouldn't matter. Just saying. So then we know that the next term is less than or equal to the previous term. So then I'm going to know that the absolute value of the sum minus a partial sum is equal to the remainder, and that's going to be less than or equal to the next term. And I know that seems really weird, but it's actually kind of a polite example. So here's our example, and it's going to say approximate the sum of the series by its first 6 terms. So we're going to use the sixth partial sum to approximate the sum of the whole series. So our a sub n is going to be a negative 1 to the n plus 1. There's our alternating part, times 1 over n factorial. So this is 1 over 1 factorial minus, that's a minus, 1 over 2 factorial plus 1 over 3 factorial minus 1 over 4 factorial, and then 1 over 5 factorial, and 1 over 6 factorial. Okay, so those are the first 6 terms of our sequence or series. And so we're going to use our alternating series test before we can use this process. So I'm going to do 1 over n plus 1 factorial. So this would be a sub n plus 1. And I'm going to show that it is less than or equal to 1 over n factorial. Okay, so this we know to be true because we can see it right here. Then as the denominators get bigger, then the next subsequent term is going to get smaller. And then if I took the limit as n approached infinity of 1 over n factorial, well, this is going to go to 0 because the degree in the denominator isn't really higher, but the numbers in the denominator are growing significantly. So then we can say, therefore, it converges. So you have to show that it converges before you can approximate the sum by the alternating series test. And our sixth partial sum is 1 minus a half plus 1/6 minus 1 over 24 plus 1 over 120 minus 1 over 720. Oops, forgot the 2. If you add all those guys together, you get 0.63194. And that's our sixth partial sum, which means it's the sum of the first six series. Well then, because I know that this is true, then I can say that S minus S sub 6 is going to equal the remainder of the first six terms, which is going to be less than or equal to the seventh term, okay? And the seventh term, so we could generate 1 over 7 factorial, and this would be equal to 1 over 5040, and that is approximately 0.0002. So this is our R, okay? This is going to be our remainder. So then I can say that S, can you see it? Yep, you can, must lie between, and I'll show you that math in just a second, between 0.63194 plus 0.0002 and 0.63194 minus 0.0002. And those numbers came from managing this portion of the equation, which says that S minus S sub 6 is going to be equal to R sub 6, and then S minus, oops, that's supposed to be an S sub 6 is, sorry, I'll change the other sign. So that's a minus is equal to a negative R sub 6. And so then that's where I have plus and minus the error or the remainder. And so then I can solve for S in each of those equations. So that's not so bad. Alrighty, that is it for today. Nice short little video. I will see you soon.